Now that we've explored how binomial distributions and distributions of p hat behave with different values of n and p, it's time to get formal and decide what do we know for sure about the center shape and spread of the sampling distribution of p hat without always having to do a simulation, because we're not going to do a simulation for every problem. So what do we know for sure? So first of all, let's recall what we know about the binomial distribution. The binomial distribution told us the probability of getting x successes in a fixed number of trials n, and it has the mean n times p and a standard deviation of the square root of npq. We did that back in our probability chapter. The conditions for using the binomial distribution was that trials had to be independent with the same probability of success on each trial. But trials aren't always independent because very often we're sampling from a population without replacement, and every time you draw one person or one individual from the population, the probability of drawing the next individual will change slightly. But the 10% condition tells us that if we sample without replacement, the probability actually changes with each trial, but we were able to still consider the trials independent if the sample size is less than 10% of the population size, because the difference in probability would be so small, it would be very little difference. So if this condition were met, then these mean and standard deviation are accurate. Now the facts about the sampling distribution of p hat, how is that related to the binomial distribution? Well, first of all, for both of them, the underlying variable is categorical. We are counting the number of times something happens. We aren't measuring something like a weight or a height, that has different values. We're just counting occurrences of something. So we can turn the number of counts of something, the number of successes in a sample, into a proportion just by dividing by the sample size. So p hat is x, the number of successes, divided by n, the sample size. So recall that a proportion is the only statistic that we can measure with the categorical variables, what percent of the time something happens. So if we look at the relationship between the binomial distribution, which is a distribution of x, and then the distribution of p hat, all we're doing is dividing everything by n. So the mean or mu of p hat is just the mean of x divided by n. So it's np divided by n, which is just p. And this is something we observed in our simulation, was that the distribution of sample p hats always clustered around or were centered at the population proportion. So the distribution of sample proportions is the population, or sorry, I should say the mean of the sample proportions is the population proportion. Now standard deviation, same thing. Sigma of p hat is just sigma of x over n. So it's the square root of npq over n. Now if we do a little bit of algebra here, this would be the square root of npq over n squared. Also remember that q is equal to 1 minus p, so on the formula sheet you'll see p times 1 minus p instead of pq. But this is just a shorter way to write it. This simplifies then to the square root of pq over n. And remember, the condition that has to be met for this to be true is that the trials are independent. So this standard deviation is based on probabilities, and probabilities are assuming that trials are independent, or the 10% condition is met. This is if you're sampling without replacement. If you're sampling without replacement, then we have to verify that the sample size n is less than or equal to 10%. I'll just write 0.10, or 1/10 of the population size, capital N. Sample size less than 10% of the population size. Now the shape. We saw that the shape of a binomial distribution wasn't always symmetric. Sometimes it was very skewed if the population proportion was close to 100% or close to 0%, and the sample size was small, was very skewed. So we found out there was a condition for the binomial distribution that NP and NQ both had to be greater than or equal to 10. And this is the same condition that has to be met for the distribution of sample proportions, because the shape of the distribution isn't affected by dividing by a constant. The only difference between a binomial distribution and the distribution of sample proportions is that we're dividing by n, which is a constant, the sample size. So the shape, we can say the shape of the distribution, and I'm going to actually say the sampling distribution, the shape of, well, actually I don't have to say that again, it's written up here. Facts about the sampling distribution of p hat. The shape is approximately normal if this condition is met right here. So now we have a normal model with a certain mean and a certain standard deviation. We know how to do things with normal models. Now realize it's not perfectly normal, it's approximately normal, but it's good enough for our purposes if these conditions are met. So now if I'm looking at a problem here, for example, suppose that I'm a great person is running for mayor of typical town, and she actually has the support of 55% of the voting age population in typical town. A local newspaper takes a random sample of 80 people from the voting age population and asks them how they intend to vote. How likely is it that the poll would predict defeat for Miss Great Person? Well, the poll would predict defeat if the proportion, the p hat of the sample, is less than 50%. So if we get a sample proportion that's less than 50%, that would predict defeat. So what we want to know is, if the population proportion is 55%, how likely is it to get a sample of 80 individuals in which the population or the sample proportion is 50% or less? Okay, so here we have p is equal to 0.55. We want to know the probability that p hat is less than 0.5. So we need to have a model to help us figure this out, and we want to know the model that shows how, if we were to take lots and lots of samples of size 80 from this population, how the p hats would vary from one another. How much would they vary? Where would they be centered? We want to create a normal model using our p hats. So we have to verify that the two conditions are true that we have up above here, and if they are, then we know the mean and standard deviation of this normal model. So let's see how likely they are to be true. So let's think of our conditions here. First of all, we have a sample size of 80. The sample has to be less than 10% of the population size. So we have to have at least 800 in the voting age population in this town. That seems reasonable. So I'm going to say it seems reasonable that the population is at least 800. Okay. So in other words, 80 is less than 10% of the population. Okay, so that seems reasonable. Number two, are NP and NQ both greater than 10? Well, N is equal to 80, and P is equal to 0.55, and Q is 1 minus P, which is 0.45. So NP is equal to 80 times 0.55, and NQ is equal to 80 times 0.45, both of which are clearly greater than 10. Okay, about a little more than 50% of 80, a little less than 50% of 80. They're both, you know, around 30 to 50 something. So that has been met too. So we can use a normal model for p hat with mu of p hat is equal to 0.55, and sigma of p hat is equal to the square root of 0.55 times 0.45, all divided by the sample size of 80, and this turns out to be 0.0556. So to calculate my probability, I'm using the normal model, 0.55, 0.0556, and I want to know, if this is the 0.55, I want to know the probability that p hat is less than 0.5. Okay, so remember, these are all p hats in here. This is just a whole distribution of p hats. These are not individual people, these are sample proportions that I'm looking at. So the probability that p hat is less than 0.5, I'm going to use the normal CDF that I've done so many times before. My left bound is negative infinity, right bound is 0.5, mean is 0.55, standard deviation 0.0556, and that ends up equaling 0.184. So there's an 18.4% chance that, given a population proportion of 55% who support I'm a great person, the poll would still predict defeat for her. There is about an 18.4% chance that the poll would predict defeat for Ms. G. So this is how we can use a normal model for the distribution of sample proportions to make a decision about how likely some proportion is to occur from a given population. This kind of reasoning is what we're going to be doing all throughout second semester with various statistics and models for those statistics.